It's great to be here. Thank you for having me. This is a big honor to come and speak to you. We're talking today about profiling and benchmarking with an eye towards making your slow code a little bit faster. So feel free to follow me on social media or GitHub. I'm not like super active on those platforms, but I'm there. Also, check out this, I don't know if you can see it, this awesome palm tree R shirt that my wife just made me about 10 minutes ago for this talk. It's just a Southern California theme, so that's what we're going with. Okay, there we go. So a little bit about me before we get started. So like Amy said, I'm coming to you from the Chicago area, the western suburbs. I found this picture in my parents' basement, so I just had to throw it in here. This is my family in the mid 1980s. Times were good, and this is my family today, as of last year. So a few changes have happened, and of course that very handsome baby, that one is me. So I mentioned I'm not super active on GitHub right now. I've got a bunch of side projects, and unfortunately they're not things that I can commit to GitHub, but there they are. Those are my kids. So yeah, I do have a California connection. I got my master's in biostatistics in 2014 from UC Davis. Right after that, I ended up moving to Illinois. I had actually married a Californian, a Southern Californian. She grew up in Simi Valley. I was really hoping that would be my ticket to staying in California forever, but it didn't work out. So here I am. That's me. And I've been using R since about 2013, where I learned it at Davis. But enough about me. Let's talk about why we're here. So I don't know about you, but I roll my eyes whenever someone tells me that R is a slow language. Maybe you've heard that oftentimes among people who don't actually use R that often, but it's a common stereotype. But at the same time, R code can be slow if we aren't careful. So, and that's because in R, we're free to achieve our objectives in many different ways. And that freedom comes at a cost, and it's sort of up to us to understand the computational intensity of our methods. So we have to have this computational awareness. And if you've been around R for even a short while, you may have heard this quotation from John Chambers a long time ago. He said, to understand computations in R, two slogans are helpful. Everything that exists is an object, and everything that happens is a function call. So why do we care about this? Well, objects are things that use memory, and functions are things that use processing power, both of which affect the performance of our code. So when we talk about writing more efficient code, we generally start by addressing the second slogan first, and that means writing better functions. So writing functions that are fast. Of course, memory is an issue too, and we'll talk about that in a bit. All right, so it's safe to assume that we're talking about code being slow. Probably Hadley can save us. He of course wrote this book called Advanced R. He says, before you can make your code faster, you need to figure out what's making it slow. This sounds easy, but it's not. Even experienced programmers have a hard time identifying bottlenecks in their code. Okay, so the answer is not actually always that clear, and it's not always something that a machine is going to be able to figure out for us. But the machines can help, and we do have tools that we can use. And also, it's okay for the process of understanding our code and figuring out where it's slow to feel challenging and confusing at times. R is such a high-level language, and there's a lot going on behind the scenes. Not much of that is really easy to understand. I know I don't understand a lot of it, even though I've been working with R for a long time. But again, we have tools to help us. Let's just pause and admire the bow tie real quick, because that's a good look. All right, so how do we actually see the computational cost of our code? And that is profiling. Profiling is the primary tool for understanding the performance of our code. We generate a profile of a function to understand what is going on under the hood in minute detail. Okay, so the question is, what is a profile? So we'll define a profile as R's estimate of the resources consumed during the execution of code. To build a profile, R inspects the call stack many times per second and logs the current function and memory allocation that it sees each time it inspects that call stack. Okay, so to understand a profile, we need a better picture of what the call stack is. Let's take a look at that. All right, so a call stack is a record of all of the functions that another function called to get its job done. I'm going to kind of oversimplify things a little bit here, but I'll give you an example to kind of help us understand how profiling works. So let's just say that we're looking to buy a house. Mortgage rates are at an all-time low, right? So let's just pretend. So we could describe the steps of touring a house with various function calls. So for example, when we tour the house, we might tour both the first floor and the second floor. Okay, when we tour the first floor, we might survey the kitchen and then check the garage, admire the backyard. Having done that, we move on to the second floor where we view the bathrooms and view the bedrooms and inspect the bathroom. Okay, so now let's think about how we might visualize this process. You can think of the house tour as a nested set of activities that, and then from there we can build a visual representation out of these individual blocks. So let's lay out the overall tour as one big block that encompasses all of the activities. Okay, so similarly, let's lay out the tour of the first floor as one part of the overall house tour, and then going a step further, stack each step of the first floor tour on top of that block. Okay, so we're basically building a schematic of the tour from these blocks. Now in the same way, we can lay out the rest of our visit by stacking blocks for the upstairs tour and further dividing that into its individual components. We've now visualized the whole tour as a hierarchy of activities. In real code, it's important to keep in mind that functions are constantly calling other functions, and that kind of creates this stack of function calls that are kind of nested like this. Now, here the call stack forms a nice rectangle in the example I've given, but bear in mind that more convoluted or nested call stacks might have different shapes, and you might actually see peaks and valleys depending on the depth of certain function calls. We'll see that in a second. Okay, but the overall idea is that in profiling, R is sort of using its power to peer into this call stack and figure out just how long each step is taking and how much memory is being used up. Feels a little bit like dark magic. So Sauron is peeking into our call stack here. So how are we actually going to get a profile? The R community gives us a few options. Even some that ship with R, like the utils package, has some basic profiling functionality. Prof Tools is a good option from Luke Tierney. He's been around R for a long time, so he knows what he's doing. It's got a lot of nice visualization features as well. I mentioned nested call stacks, and if you look at the documentation for Prof Tools, you can see this is one example here where you kind of have this very deeply nested kind of call stack here, and this is just kind of one cool example that he provides in his documentation. I'm going to focus here on ProfViz for its simplicity, but also for its integration with RStudio, which makes it really nice. It's maintained by Winston Chang. So let's take a closer look at the ProfViz package. Let's look at the main function, which is conveniently called ProfViz. And it's got a bunch of arguments, but the most important one is the expression argument, which is the code you want to profile. And that's usually a function that you yourself have written. The other main argument is the time interval in seconds at which you want to sample the call stack. And that's usually a pretty small number. And then there's some other stuff, including output options, memory management, and other stuff that you should take a look at on your own time. Okay, so to use this function, you would give the expression argument a function that you wrote. So you just have this function that's running too long, and then a sampling interval. So the default for the sampling interval is 1/100th of a second, and that works pretty well. So normally you wouldn't have to change this. This just means every 1/100th of a second, R is examining your call stack and seeing where you are, which function is being executed, how much memory is being used. Okay, so this is all it really takes to run this function. Now we're going to look at how this thing actually works in practice. Okay, so live demo time. Brace yourselves. Anything could happen. I'm going to flip over to my R Studio here and just quickly check, can everybody still see this?
Yes.
Okay, thank you. All right, so here I've written the same house tour functions that we saw earlier.
We can't see your R Studio, sorry.
Oh, okay, sorry. Let me stop sharing them and reshare.
Stop sharing and then reshare.
Yep, I shared the wrong thing. So.
I only know this because I make that mistake the other day. To be honest.
So that meant you couldn't see the. Sorry, this was the visual of the Prof Tools package I was trying to show earlier with the peaks and valleys. So this is like a graph that might come out of Luke Tierney's Prof Tools package. Sorry, you couldn't see that. Okay. So anyway.
Adam,
yes.
Karina has a question in chat.
Oh, sure. Yeah, what is it?
She wants to see the expressions again. Show the slide with the argument definitions again.
Yeah, for sure. Yep.
Looking at chat. Somebody should be.
Thank you.
Yeah.
So let's look at the. So this is just like a high-level view of what the arguments are for prof is. So you have an expression, which is your code to profile, and usually you're just passing it a function, and I'll show you how that works in a second. And then you have the time interval, and then you have a bunch of other stuff. And I would totally encourage you to go to the prof.is documentation and see what that other stuff is that helps you manage like what kind of output you get, how you handle the memory management, things like that. There's a ton of options there, so go check that out. The time interval has a default, so you don't have to change this. I think the default there, 0.01, is pretty reasonable. So you can usually keep that for the most part. But otherwise, you're just passing a function to that expr argument. So let me just show you how it works, because it'll all become clear if it's still confusing. Okay. So what I've done here is I've written out this house tour, right? So we have the tour first floor, the tour upstairs, and again, the tour first floor consists of 3 parts. You're looking at the kitchen, the garage, and the backyard. And then when you go upstairs, you're viewing the bedrooms and the bathroom. So it's just kind of a nested set of function calls. Most of these things are taking 1 second. I've written them to just create a system pause of 1/10 of a second. And except for inspecting the bathroom, where I've written that to take a system pause of 3/10 of a second. Maybe you're like really into plumbing and you just want to make sure everything's good. So you're spending a lot of time scoping out the bathroom. It's very important. Okay. So these functions, as you can see, they're not computing anything or returning any objects. It's just for illustrative purposes, so that when I show you how prof.is works, you get a good sense of what's going on. Okay. I'm going to flip over to a different script now that's just going to run this tour. So let's just focus on this top block here, and I'm actually going to blow this up a little bit just to make it a little easier to read. All right, so I'm going to source my house touring code. Okay, so all those functions are loaded up. And now all I'm going to do is call prof.is, and I'm just going to pass it the top level function, tour house. That's the whole thing. And that's all I'm going to do. And it's going to run a profile. And now some magic happened. Okay, the result here is a nice summary of the action in a new R Studio pane. And actually what's cool about this is you can pop this out. You can either just pop this out as its own like R Studio window, or you can open it in a browser. So that's what I'm gonna do. I'm just gonna open this in the browser. And I'm gonna blow this up so you can all see it. Okay, so right away, you'll notice a couple things. You've got kind of 2 panes in this viewer. At the top, you've got all the code that I sourced. So, these are all the functions that I wrote, and all these functions ran, and that's what is being represented here. And on the right now, you'll see a memory column and a time column. And these provide a graphical view of memory usage and time spent in different parts of the script. The script didn't generate any objects, so no memory was consumed. So this is empty right now. We'll fill that later. But on the right, you do see the function did take time, and that's what is being shown here on the right. Okay. So on the bottom pane, we now have a call stack that looks very similar to the one we drew earlier. This thing down here, right? It was that rectangular call stack I showed you earlier in the slides. So when building the profile, R inspected my call stack and built this view based on the structure and the timing of our functions. This representation down here is called a flame graph because of the flame-like shape it sometimes takes when displaying complicated call stacks. So Remember this, this view here from Prof Tools. This is also called a flame graph because it looks kind of like tongues of fire shooting up. So what you should notice here is in the flame graph now on the x-axis, we have the total runtime of the function in milliseconds. So this whole thing took about 700 milliseconds, okay? And in fact, the horizontal distance of each piece of this graph indicates how long that section took. So recall most of our functions were designed to take about 100 milliseconds. So that would be here. In this case, it clocked it at 90. But of course, inspecting the bathroom was meant to take longer. It's like this just froze up on me. Okay. Anyways, inspecting the bathroom took a little longer, so 300 milliseconds. And as I move my mouse over various sections of these functions, except, of course, this is a live demo. Things are breaking. Okay. As I'm moving my mouse around, you can see that it's highlighting different parts of my top pane, and so it's linking the top pane to the bottom pane, so you can kind of get a clearer view of where each function call was happening and how long these things took. So one more nice feature that I want to point out in this view, and that's the data tab. So here we're looking at the flame graph tab up top. There's also a data tab. Okay, so I'm going to click this, and it provides an expandable hierarchical view of the call stack. So the top level function we called was tour house, took about 700 milliseconds. But I can expand that, and I can look at the upstairs tour and the first floor tour. So upstairs took about 400 milliseconds overall. And I can expand that further and break it down and look at the individual pieces. Okay, so this is a really nice way. You know, sometimes your functions are super complicated and this is hard to read, but a lot of times this is actually a really nice way to view your memory and time usage. And so this is a pretty simple and contrived example. I do want to show you what this might look like in a real world scenario where you write a loop that you don't really need. So let me go back to my code and let's go to, all right, this is a function I wrote that takes a square root. The function is called take square root. So it takes a square root of a vector. The way I've chosen to do this is intentionally bad. It takes the square root of the first element of the input, okay, and assigns it to x, and then it iterates over all the other elements of the input and grows this vector. So if you've been coding in R for even a brief amount of time, you probably learned this is not the right way to do this, but we're going to try it just to see what happens. So let's look at this. Let's see what happens from a profiling standpoint when we grow a vector in an inefficient way. What I'm going to do is I'm going to source that code. So now I have that square root function, and I'm going to take the square root of this big long vector and cross your fingers that this runs. It takes a little bit. So I just want to make sure I capture all the weirdness that goes on. Okay, something's happening. There it is. All right, I'm going to pop this out and blow it up so you can see it. All right, so let's do that. All right, so, okay, right away there are a couple signs here that we might have a problem. So the first is at the top pane, we see not just a long runtime, but we also see a lot happening with the memory. There's actually a fair amount of memory allocation on the right and deallocation on the left. Okay, and this tells us that R spent a lot of effort creating objects and then cleaning them up, which is pretty inefficient. Okay, and you can also see the flame graph down here is a huge mess. It's really hard to read. It's hard to tell what's going on. You can actually zoom in on these things, which is really cool. It's a nice like interactive interface. So I'm just kind of like using a scroll wheel and zooming in, enlarging certain sections. And what you can see is there's a lot of calls to GC, which stands for garbage collection. Too many garbage collection steps tells you that R is working really hard to allocate blocks of memory and then get rid of them when it doesn't need them anymore. So R is actually copying our vector every time it's adding a new element. So it's using way more memory than it needs to actually take the square root. You probably could have guessed that by looking at the way the function is written. So of course you'd be much better off using R's vectorization to accomplish the same thing this function was doing, but this interesting example of what a bad function call might look like. You can look at the data view here too, and you can kind of see where all of the problems were. So there's memory management and there's time consumed in this for block here, but most of the problem here is actually in this vector drawing stuff. Okay, so that's not too surprising, I hope. Get rid of that, and I am going to flip back to our presentation. And how are we doing on time? I think we're okay. All right, so I want to talk about a few ways things could go wrong and how you might actually speed your code up. And I'm not necessarily suggesting that you would find yourself doing some of these things, because some of these are pretty contrived examples, but just to illustrate where some of the problems are lurking that maybe you're not thinking about when you're writing some of your code. So extraneous for loops kind of goes hand in hand with what we just saw. In some languages, the way you might total up a vector is by looping over the elements of that vector and just initializing some kind of total variable to 0, and then just continuing to sum up your total plus the newest input and reassign, overwriting your old total object there, and that's might be how you would take a sum, for example. Of course, we know that's not the best way to do it. In R, thank goodness, we just have this sum function. So you just take your input, you throw it into sum, and then what's happening is, of course, we have these built-in vectorized functions that call C code under the hood and run their loops super fast. So that's what's happening here. There's a ton of really interesting loops. And if you go digging around the R documentation, you can find some of these cool ones. So like not only is there sum, which is returning a single number, but you have cum sum, which is the cumulative sum. As you iterate over the vector, you generate a cumulative sum. There's prod, which is a product. Cum prod, it's the same thing as cum sum, but iterates and takes the product each time. And then there's all kinds of really interesting loops that are built in and are way faster than anything that you can accomplish in a for loop. So, for example, column means is going to take the means of all your columns. Row means the means of all your rows. Cool stuff like that. All right. Go to the next level. Speed bumps 201. Memory not allocated. Okay, so we actually dug into this in our live demo with the square root function. So sometimes, if you initialize the value of an output to just a single value, and then you iterate over a vector and you grow your vector, that's a problem for memory allocation. Right. There are a whole series of ways you can do this better. You can either pre-allocate your vector before entering the for loop. That's totally valid. You can use members of the apply family, which pre-allocate memory, so R doesn't repeatedly make new copies of the vector. And there's a whole host of apply family functions. They're running out of letters. I don't even know what all these things do, but go and check them out. They might be applicable to your situation. This vapply function is actually pretty slick. I learned about this in a workshop from Hadley Wickham himself. So this is kind of cool. If you know that the output of your function is, for example, a numeric value, you can actually specify what type of output R should expect. And that does two really cool things for you. If you loop over some input and apply some function, and the output doesn't match what you expect, it throws a really helpful error, and you'll be able to track down where that problem happens way more easily. The other thing it does is because you're pre-specifying what R should expect, R doesn't have to take the extra step of interpreting your output every time and checking the output against the vector you've already created to see if the output vector should remain the same class. And so you're actually getting a speed boost by specifying that class up front. So kind of a cool trick.
Adam,
yeah, talk to me.
Someone actually had a question in the chat for 201.
Sure.
Why is the output down in 2 steps? Let me see. Can you see the chat?
Let me see. Where is the chat? Oh, there it is. I feel like an old person. Grandma, where's the chat?
Oh,
Okay.
Question is, why are you using output
yeah,
and then output I?
Oh, right. Yeah, this was right. So this was to show an example of what you wouldn't want to do. So output. So the first thing I'm doing is I've got some kind of input vector, and I'm just calling a function on it and saying call the function on the first element of the vector, and that's my output. And now I've got this single valued output. And now I'm going to grow the rest of my output vector one element at a time by forcing this kind of this subset to say, like, okay, now I want the second element of my output to be the application of some function on the second element of my input. And I'm just kind of growing the vector one element at a time. I don't know if that helps.
And also, your microphone kind of, I think it's a little bit unclear when you touch the computer.
Oh, sorry. Hands off.
Okay.
Maybe,
Yeah,
maybe because
thanks.
your microphone, the wire is shaking. Maybe touch the computer sometime. I'm not sure.
Okay. Yeah. Sorry. I'll try to be more gentle on it. I get so excited. Okay. Shall I move on?
Yes, please.
Okay. Sweet. So this one is kind of interesting. Too much subsetting. It's a little bit sneaky. So maybe just hypothetically, you read in a data frame, and it just happens that for whatever reason you've got a whole bunch of like columns that were read in as characters, and you want to convert them all to integers, something like that. Perhaps you've iterated over columns and forced a new type on those columns. This is one way to do it. So you can say, for my column, in each of my column names, I'm going to overwrite that column by forcing a new type of that column. This is a valid way to replace columns with the same data but a new class, right? So maybe you don't want them to be numerics, you want them to be integers, for example, or whatever it is. This is actually kind of cool. What you can do is use this empty bracket subsetting trick, and you can actually loop. You can still loop. Let's use an lapply in this case. You can do an lapply over your data frame, and then do your type coercion. But now you're storing it here back to the original data frame using this empty bracket subsetting, and that just means the empty brackets mean preserve the class when you return the output. So normally, if you're calling this lapply, you're getting a list back. That's what the L stands for. So normally you would get back a list of each column now as an integer, but it's in list format. But this empty square bracket subsetting is actually forcing it to retain the class. So this is kind of like a weird esoteric trick, but if you ever do have to do something like this actually creates a huge speed boost. But square bracket subsetting can also be used for other purposes in replacement. So to selectively replace values in a vector, for example, you might use different subsetting conditions if you wanted to replace values that were NA or that were infinite or that were equal to some value or not equal to some value. Right? You don't have to write a loop and check each individual value of that vector and then replace it if some condition is true in that one specific value. You just use square bracket assignment and you subset the vector according to some condition and then just overwrite all of the values that have that condition with some new value. Okay, so this is pretty slick. You don't have to do a for loop for this. You can just use square bracket subsetting. I remember I started my analytics life in economics, and we were using Stata, and Stata stores missing values as minus infinity, and that just drove us crazy. Because if you wanted to like take all the values that were less than something you would get not only all the values, less than 10, but also all of the missing values, because those were minus infinity, which were also less than 10. Nuts. So anyway, if you had something crazy like that, you could replace all the values that had some kind of infinite value with something else. Okay, this is one of my favorites. Speed bumps 401. Sneaky functions. Sometimes you can feel like you're doing all the right things, but you still end up with slow code. And this just kind of goes to show that life isn't fair. But everything that happens in R is a function call. Even things you don't expect to be function calls are function calls. So let me show you an example here. So here in this top block here, we're looping over some vector y, and we're calling a function from a package with this canonical package name ; function kind of syntax. Okay, and actually what happens is that is not the optimal way to do that from a speed perspective. The best way to do that would be to load the package first and not call the namespace directly with the 2 colons, because everything that happens in R is a function call, even those 2 colons. That's also a function call. A lot of sneaky functions. Not all of these things take a lot of time to execute, so that's not always a huge deal. But if you are running code over and over and over again and using a lot of these functions like $, or some kind of like assignment step where you're replacing something in square brackets, that it's a function call and it takes time to execute. It takes time for R to interpret that. So just be aware of these things. If we have time later, because I'm running out of time, I will actually show you how this double colon can be a problem if you call it too many times, because it does actually end up taking a lot of time. It's kind of surprising. Okay, I gotta move on. But questions you should ask yourself: do you even need to optimize? So if you've run a profile and broken a function down, that's the time to stop and decide whether there's any point in making it faster, right? So there's a lot of questions here on the left, but basically the idea is if the function is being called once, and maybe you run the process once a month or something, and you think you can shave off like 30 seconds or something from the function call, out of a whole period of like a 2-hour process. It doesn't really need to be optimized at that point. That being said, now if you have a very slow function you're calling over and over and over again, that's when you need to start thinking about optimization and speeding up your code. It takes time. It's an investment. So you just have to decide if it's worth it. Okay, profiling has a few limitations. A profile is not deterministic, which means that every time you run it, you might get different results, slightly different results. They'll be more or less similar, but you can't expect to get identical results every time, just because R is checking in at very frequent intervals, and because of the way processors work, you just might be in a slightly different place each time R is checking in. Okay, if you write with a lot of anonymous functions, you can write a lot of anonymous functions inside the sapply or lapply or any of the apply families. Those can't be distinguished from one another. So if you have a bunch of those kind of all squished together in your code, it might be hard to tell what's going on. Lazy evaluation might make the call stack hard to interpret. So you think a function is being called in one part of your script.
Oh no, did he freeze?
I think he froze.
Oh no.
Now you know how they work.
Let me see.
Yeah, Amy.
Yeah, you froze.
Oh, I froze. Oh, sorry.
Yeah. Oh, you're back
Am I
now.
back?
Yeah.
Okay, cool.
I think we lost you right at lazy evaluation.
Okay. Yeah, lazy evaluation just basically means, R is only going to execute code when it decides it needs to. So if you expect a function to be executed in one part of the overall process, but it actually doesn't get executed until much later because it isn't called until it's needed, that might be confusing. And then the usual profiling tools will not help you with compiled code like C++ code. So I don't actually know how to profile those. That's outside my expertise, so I'm not even going to comment any further, but profiling won't help you with that. All right, so let's say that we've profiled a function and we've decided that we found a big source of our problem and we want to know now how to make it better. So profiling helped us find bottlenecks in a sequence of steps of our function. Benchmarking is going to help us compare alternative approaches to one of those individual steps. If we found our bottleneck and we want to just target that one specific piece of code and find something that's better, that's where benchmarking comes in. Okay, so it's called benchmarking. It might be called micro benchmarking in some contexts. It's kind of the same thing. But basically, a micro benchmark or a benchmark, it's a performance comparison of different functions that accomplish the same thing. Benchmarks provide the timing of small, specific, and relatively short pieces of code. If you hear micro benchmark, it sounds fancy. It's just a way to say you're timing your functions. That's all it is. All right, let's take a quick look at the benchmarking packages. These are all in CRAN. You've got base, kind of, if you want to make use of system.time, but that's not a super accurate way to do it. So there are these other options. You've got R benchmark, micro benchmark, TikTok, which is not the app, but something else. This is a benchmarking package. And then there's a package called Bench. There's tons of choices here. Look into all these, they're all good. So, you know, in your spare time, go out and decide what meets your needs. I'm going to focus on Bench because it's pretty easy to use. It has a nice, nice outputs. So here is what the Bench package looks like. The central function in the Bench package is this function called mark, because it's cutesy, because you get to say bench mark when you write it this way. So the first argument here is the 3 dots. So here you would pass comma-separated expressions to benchmark. I'll show you what I mean in a second. There's also a min time argument, and this is the minimum number of seconds to run each expression. So benchmark is actually running your expressions over and over and over and over again to get a good estimate of the average time it takes to run those expressions. Okay, there's a bunch of other stuff in there too, like iteration counts, memory management, and please feel free to look at those in your spare time. So this is what I mean by passing comma-separated functions for the dots. So instead of dots, you would just put as many functions as you want to benchmark together, separated by commas. Okay. The default value for the minimum runtime is ½ a second. That runs fine for most cases. If you've got a super long running function, you can change this. You can make it longer if you need to. Okay. So yeah, again, add as many functions as you require. Let's continue with our example from earlier when we took a square root. If you recall, we took a square root using a really poor approach. All right, so let's say we did some research. We learned that we can use vectorization to take the square root, but now we want to know which approach is going to be fastest. So we could just pass in our different approaches to this mark function. And again, it's important that these functions are accomplishing the same task so that we know our results are directly comparable to one another. So here, you know, just taking the square root of all the values from 1 to 1,000 in 2 different ways. All right, I know that we're real short on time, so I'm going to do a quick demo, and then I will encourage you to check out more of this on your own. But let's just look here. I have a script. I've got this input, which is just the vector 1 to 1,000, and I'm going to use my benchmark function. I am going to pass the input to the square root function. I'm going to pass the input to the caret function and just raise my input to the power 1/2. I'm going to use this fancy version just for fun, where I exponentiate and then do this fancy stuff, which is, again, the same way to take the square root. And then I'm just for fun, I'm going to use my old take square root function, which we know would be bad, just to add a little drama. Okay. I'm actually going to save the output to this object that I call BM. It's going to be a tibble, and I'll show you what it looks like. So let's run this. It just takes a quick second to run. And let me just give you a real quick, show you what the output of this function is. You know, I have to actually shrink this down a little bit. Okay, I'm gonna try this again. Show you what this looks like. All right, so it's a tibble. It's got a bunch of columns. And then what it's doing is on the left, it's showing you all the expressions that we ran. Okay, so that's here on the left. And then it gives you a median time. It runs these functions a bunch of times, and then it will compute for you the median time spent on each function. And then it will tell you, if it's nanoseconds or microseconds or milliseconds, whatever it is. Here we have microseconds. Okay, so what we can see here is the median time, the best function to use is SQRT, square root. That's the fastest time based on our median. In second place, surprisingly, is this fancy version. Our intentionally bad function is clearly bad. It has the longest runtime. There's a whole bunch of columns in this object. I want you to go and look at the documentation when you have time. I'll just show you, right? There's like the number of iterations per second you've accomplished, the number of garbage collections per second it did, things like that. It's all really great information for you to help you figure out what's going on. You can also make a plot. By default, you can use the standard plotting method to plot this benchmark object. And by default, it does this B-swarm plot, where it kind of shows you just the distribution of all the runs that it executed for each function, and it gives you a really nice idea of how fast or slow each function is. Beware that the x-axis here is on a log scale too. So you've also got other plotting options. I won't show you all of them, but there's different kinds of types you can throw in here too. So all good stuff. Okay. I took a lot of this information from Hadley's Advanced R book, so please go check it out. Here's the URL. Chapter 23 and 24 are the places to start, and you'll get some really good tips, some other cool speed up tricks that you can learn there. But until then, that was my talk, and please feel free to reach out to me on social media if you have any questions or thoughts, and happy to chat. Thank you so much for being here and for your time.
Thank you. Running a little bit over time, so how about we let the second speaker speak first, and then we can ask all the questions. Adam, are you gonna stick around, or are you gonna log off soon?
Yeah, I'll stick around for sure. I want to see this talk.
You can also
I'm excited for it.
you can also respond to the chat if you have time. But,
oh, definitely. Yeah, I can do that too.
Yeah. So let's move on to the next topic first. As I said, the next Carolus?
Yep, that's right. Can you hear me?
Yeah. Can you share your screen?
Okay.
Yeah.
Okay, 1 moment.
For everybody here, it's super early for him right now. It's like 5 a.m. and I appreciate him get up so early for this. He's in Lithuania in Europe, so welcome. And I definitely did not pronounce his name correctly. I cannot pronounce Trio, and his name is in Lithuanian if you want to check out the pronunciation.
Yeah, it's not that important. You can mispronounce it. Yeah. So I can begin, right?
Yeah. Go ahead.
Yeah, okay. So hello, everyone. So I'm really happy to be able to talk about R with people from the other side of the globe. And like Amy mentioned, I'm joining you from Lithuania. And currently here it's a bit of a middle of the night. So if I'm not as smooth as I probably should be, I hope you can take that into account and forgive me. So my talk will be about lesser used base R features. And by lesser used, I really mean things that you wouldn't stumble upon by, for example, taking R courses or even reading contemporary books about R. One note before we begin is that I will assume in this talk that you are not a complete R beginner. Otherwise, you might miss a few things. If that happens, that's fine. I will talk about 4 different topics. So if you find yourself not really following one topic, you can just wait till the second section starts and go from there. So with that said, let's begin. The first topic I would like to talk about are these infix and replacement functions. And you might find this topic interesting if the 2 lines here, the 2 first lines of code on the slide seem kind of friendly to you. And maybe the third one gives you a pause and you are a bit weirded out about it, or maybe intrigued. So if that's the case, I hope this will be helpful. So for a bit of context, let's go over the replacement functions. In R, there are these things called replacement functions, and you write a replacement function with this syntax. Basically, you have to have a special function name that ends with the assignment symbol. And when you have this function, you call it by doing an assignment to your function call. And what it does, it replaces something about X with what's in value. And in base R, we have some examples. So for example, there is a names function that changes the names of an object. You can also change the class of an object. And there are a lot more. So one may be a bit exotic is this last one where you can change the first and second element of X into NA also with this kind of syntax. So next thing that you are probably already familiar with is this infix operator syntax. Again, these are special functions and they have a special name. If you try to implement this function, you have to use this percentage signs around your function name. Once you have this function, you call it by putting your infix operator in between two variables, and the function will do something for those two variables and provide you with a result. In R, there are a few examples of those functions. So one very well known is the in operator, which checks if the element in set also appears in X. And there is also this one called outer, which basically takes a multiplication of every pairs of elements. So for example, that line, the last line of the code would provide a multiplication table. But the surprise begins when you try to combine these things. So in R, you can also write this very special function, which combines both infix syntax and replacement syntax. You do this again by having a special function name. It has both the percentage signs around the function name, as well as a assignment operator at the end. Once you have this function, you would call it like this. So you would have an infix in between your variables, and then you would assign a variable to that statement. And what it would do is it would replace a value in X based on the comparison between Y and X. So, and the surprising thing is that even though this is a valid R syntax and R allows us to construct these things, there are no examples of such functions in base R. So since there are no examples, we can now look at some of them. So this is a very simplistic one, a function you can write in R. If you look at the body, it's doing a very simple thing. It checks if Y elements are in X, and for every such element, it replaces the value in X with an optional value from this function. So just an example of how it would be used. If you have a vector with 4 elements, you can write your call like so. So you write vector, which is your variable, and then basically a standard in operator that checks if B and C is in vector, and then you assign a new value to those values found in the vector. And what it would produce is it would replace the vector, it would replace the values B and C, in this case with O. And even more surprising is you can do this not only with your custom infix operators that use, for example, percentage signs, but you can also do similar things with standard operators. So like in this example, we are using this equals operator, which just compares if 2 values are equal. But I can also add an assignment to the end of this function. And then if I have a vector now, the same vector, about 4 elements, I can call my new function like so. So I say, okay, vector equals 3. I found all the values that are equal to 3, and I replace them in this case with a 0. So what that would do is it would find elements that are equal to 3 and replace them with 0. Yeah. So after finding this functionality, I got in contact with this other person, and again, now I might mispronounce the name. So it's Antonia Fabri, as far as I know. And we worked together to create a package that basically utilizes these things. It was quite surprising that we were not able to find it used anywhere, even in external packages. So we call this package called inops. And just like a quick example of how we exploited the syntax. So in this package, we created basically a big list of various infix assignment operators. So for this example, here we have this vector of countries like USA, USA, China, 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 Russia, 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 Latvia, and Lithuania. Now, we provide various operators, and one that I particularly like is this one, which checks for elements that occur a specified number of times in the vector. So for example, if we call something like that, what it would do is it would return true only for elements that occur once in the vector. So USA occurs 2 times, China occurs 3 times, Latvia and Lithuania occurs only 1 time. So it would return true for those. Next, we can also use selection. So if we add this bracket in the beginning of our operator, we would actually select those elements. And now we also provided this new syntax that we found, which is useful for replacement. So if you write it like this, then what this would do is it would replace all the elements that occur only once within your vector with the other group. So for example, if you're doing some kind of analysis and you have many groups and you want to group all the smaller groups into one group called other, the syntax would do this in one line. Yeah, so that package has a lot of various different operators, and if you care about this thing, you can check it out. For example, we have some that work for regular expressions, for interval comparisons, and various things like that. So now moving on to the second topic, in R, there is this thing called the dollar operator. And you might find this part interesting if you feel good about the first 3 lines here, which uses the dollar operator and also auto-completion after pressing the tab key. But you are surprised that you maybe also make the tab key fix spelling mistakes for you. And if that's the case, then this talk might be interesting, this part of the talk. So yeah, let's start with explaining what the dollar operator is. So let's say we have a vector of 3 elements and the vector has names 1, 2, 3, right? The dollar operator typically works on lists and data frames. So if you would try to do something like that, it would give us a syntax error, basically. It's invalid for atomic vectors. Okay, but we can do one trick here. We can bless our vector actually with another class. So we, instead of only just being numeric, we say, okay, this vector is now not only numeric, but also has another class, which is my class. And then R provides us with this generic function, dollar symbol. And this function here is really simple, right? So we have a dollar symbol for a class of type my class, and we passed it X and name, and it simply selects that name from that X that we passed it to. And you can think about it like that. So if you write this expression in red on the right side, X dollar name, and press enter, then this function will get executed if X is of the right class. So if we now write vector $2, it will select the second element. So we made it work on our vector, our special vector in this case. But it can also be used for other things. So it can be used to do computations, not only to return elements to you. So if you now modify our function like this, what we end up with, we would not only select elements from X, but we would use the part after the dollar operator to call functions on our vector. So as an example, having a function like that, if you now call vector sum, what it would do is it would call the function sum on all the elements of the vector, and they sum to 6 here, so it would return 6. So that's surprising, okay, but there is also this part about autocompletion. So we have this vector of a new class, right? And we can call functions in it with this new dollar operator, but it for now doesn't automatically complete the names because it doesn't know what to complete. And here R has this second generic function, which might be useful, which is called dollar names. And dollar names, basically you can think about it like this. You have X, an object, you type dollar operator and start typing a pattern, and then you press the tab key. What it does is it passes X and pattern into this function, and whatever this function returns is then replaces the pattern. So here, just as a simple example, if you look at the body of this function, we create a vector of 3 character strings, basically mean, median, and sum. And then we use pattern to select one of these 3 values. So if somebody will start typing one of these 3 values, they will get autocomplete. So how this works, if we now add this new function to our R session, and we start typing back $s and press the tab, it would autocomplete to sum. And in another case, if instead of S, we started typing ME, press tab, it would see that there are 2 possible occurrences. So it will show us both mean and median. Yeah, but it doesn't have to be, this function doesn't have to make sense. So really you can put anything in there. So as a very simple example, for example, you can modify this function to always return a string whatever. And now whatever we write after the dollar operator, once you press the tab key, it will simply replace whatever was there with whatever. Or even more weirdly, what we can do is not only return character strings, but also do something crazy like maybe starting a new plot. And now if we have such a function, if we start autocompletion, press tab, it would actually show us a plot and we would have written whatever on that plot. So basically the takeaway is that you can transform this function to do anything, not just actually provide you with autocompletion. And where can this be used, for example, in practice, besides, of course, writing your own custom classes, is it can be used to modify how autocompletion works for data frames. So if we now write this function $names.data.frame, we will be implementing a generic for the data frame class. And here I try to use this agrep function. And agrep is very similar to grep. It tries to look for patterns, but it's not really exact. So you can have mistakes in there. So if you, for example, looked at the third argument there, max distance, it specifies how much of a mismatch the function tolerates. Then we also add ignore case because we want to autocomplete even if we put the wrong case there, and value equals true, just so it returns the value to us. So anyway, if we put this function to R, and then we start with this famous iris data set, press the dollar operator or start typing something closely resembling one of the columns like Z, B, C, press tab, and it will correct our mistakes and it will know that the closest column to what we wanted to find is PCs, so it will autocomplete. Yep, so that's about dollar operator. Now, the next thing is plotting hooks. Now, you might be familiar with the concept of a hook if you use packages like maybe knitr, but you might be surprised to find that base R also has this concept and it uses it in a few places. So here we will see as an example hooks introduced into plotting operations. So like I mentioned already, hooks is a mechanism for injecting function after a specific action within R takes place. So if you looked at for the code for the function plot new, you would find that there are 2 hooks defined there. So within the first loop, you can see that it calls getHook before plot new. And this getHook method would extract all the functions defined in that hook, and this loop then would iterate over all those functions and call them in turn. And likewise, you have, after the plot is created, the second hook, plot new, which does the same, but only for a different hook now. So we will just create a simple example to demonstrate how this works in practice. So let's say we have a simple function add date. This is base R function, so it's base R plotting. And what it does, it adds the current date on top of the plot you are creating. So this mtext is marginal text, and it puts system date in the margin on the top of the plot. Yeah, simple function. And then we call this set hook mechanism. So how it works is we provide the hook we want to set, in this case plot new, one of those plot hooks. We provide our function we want to add into that place, and we said append. So if there were any functions before us, we would not replace them, but append to them. And now after we've done this, we can call, for example, plot or pie. And the result would be that you can see that on the top right corner there, now there are these dates printed on the plots. And whatever plot I do in the search session from now on will always have the date on top. So that's a hook. And when I found this mechanism, I kind of thought, okay, how can I exploit this? So I think I came up with is that it can be used to provide a theming system, a very convenient theming system for base R plots. So I created this package base theme just to test if this works. And on the left side here, you see a default pairs plot, which is a simple plot in base R that provides scatter plots for all pairs of variables. And on the right side, there is the same plot after you change the theme using this hook operation. So the concept of this package is very simple. I basically add functions that change graphical details, and I then add them to the hooks before the plot is called. So whenever somebody produces any kind of plot, they will always call that hook just before the plot, and it will set various graphical parameters before the plot appears on the screen. So just a quick another demonstration. Imagine you have some kind of a report that looks maybe something like this. What it allows you to do is set the theme once, and then it will apply that theme to whatever plot you do in R, in base plot, not for grid package. So, for example, if you got bored of this look, you might say, okay, maybe I want to try another theme, and all you would have to change is that one call. You change the name, different theme will be applied to all of your plots. And this is persistent, which means you don't have to apply a theme to each plot. You set it once, and the hook is there, and it will work from now on in that R session forever until you close R. So that's how I try to exploit this mechanism. And the final topic of this talk is the base plotting itself. So many people, even if they use ggplot actually, sometimes they do a plot or two in base plotting because there are some functions that are maybe more convenient. So if you are that person and you, for example, know about functions like plot or hist, but are a bit confused about maybe the last two lines, you might find this part interesting. So if you go over a new user's experience with base R plotting, we can imagine it to be something like that. They have a goal, like maybe they want to create a very minimal picture that has a histogram on top of a density plot. And they would probably go about it like that, right? They find that you can plot density objects directly. So they start like that. And okay, so they now don't like that title. They want it removed. So they find there is an argument which turns off the main. But they maybe want to do the same for all the access labels actually. So they find 2 additional arguments, okay. But there is still too much in this plot. They want it to be minimal. They want just the density lines without this axis. So they find a way to turn off them as well, okay. Now they find another function called hist. And they think, okay, if I call hist, it will be added on top of my density function, but it's not the case. And actually they, at this point, would be confused why you call plot to plot density, but there is a special function, hist, for histogram, why it works a different way, right? Okay, so they now replace their plot, but they wanted to add on top of it. So maybe they, will search Stack Overflow and find that there is this parameter add equals true, which adds on top of the plot. Okay, so now it's added, but the histogram is too big. After another search on Google or someplace, they might find another parameter, which is freak. And that makes histogram bars resemble the values in the density plot. That's fine. Maybe they also like more breaks, so they find parameter for that. And now they still see that, okay, the plots are on top of each other, but the histogram hides basically the density plot. So maybe they find some colors, adjust transparency, and now it shines true. They can even increase the line size of the density plot. Okay, that's fine. One more thing is probably that it looks like the histogram goes over the top of the plot. So they manually adjust the y-axis limits. And okay, looks like right now they have their plot. But if they remember this experience, they would think of base plotting as being kind of really bloated and weird. And my God, if I actually wanted to add more than one histogram on top of here, it would be hell, right? I would have to, again, call one function, set add equals true, and somehow align all these bars within them. It's basically tough and it's clunky, right? You not really are working with base graphics at this point, but more so fighting against them. The files that you get do too much and you spend a lot of time trying to turn them off, basically. Yeah, so your conclusion would be that, okay, base R graphics is bloated, unintuitive, weird, and hard. But maybe, not so fast here. So I will try to defend base graphics a bit during this part. So one thing to state outright is that those plots like plot, hist, they are really wrappers. So they are very high level functions. And under the hood, they call a lot of small functions that are really intuitive and work very well with one another. So let's take a simple example. If you do this, like plot 0, 10, 0, 10, you will get a scatter plot, a simple scatter plot. But even this plot is actually, like I said, a wrapper around a lot of different things. So if we were to reconstruct this one by one with the actual functions that do all the work, we would see something like that. We would first start with the plot new, which just creates a new empty plotting device. Then we would call another function plot window, and this plot window overlays a coordinate system on top of our new device. So if you want to add a point on top of the plot, we need to know which place of the plot corresponds to which x and y coordinate. So we basically add Cartesian coordinates on the plotting region with this function. And then we can start adding things on top. So for example, we might do points and it will add points. Then we can create an axis. So axis 1 for the x-axis, axis 2 for the y-axis. And actually here, you might wonder about the numbers, what those 1 and 2 means. So 1 basically refers to the bottom of the plot, and the numbering goes clockwise. So 1 is the bottom of the plot, 2 would be left side, 3 would be top, 4 would be right side. And these numbers are used throughout various different parameters. So here we use them with axis. So we had axis, then okay, there were also a box around the plot, was also a box around the plot. So we added with another function called box. Then titles are missing. So, okay, we had the title, my plot, okay, a title for the x-axis and title for the y-axis. And we recreated the plot we had before. But now, when we put it like this, everything becomes really clear. For example, if you have a friend who doesn't know anything about programming or maybe even anything about R, and you ask him which line does what on this plot, they would have no trouble telling you. Axis is added by axis, points added by points, box around the plot added by box, titles added by titles. So once you have it like this, we might try changing a few parameters. So what we would do is maybe, okay, what can we do? So we can add grid to it with the function grid. Now we have a grid. We might say, okay, we can adjust the title. Like if you look between these two, the title moved to the left. Then, okay, maybe we increase the font of the axis numbers. Maybe we don't need the box around the plot. We turn it up. We might say, okay, we don't need these axis lines anymore. They're nice. We can make the axis labels maybe a different color. We can increase the point size and stuff like that. So you, of course, would need to know the parameters, but it's trivial to see which line has to be modified in order to change certain elements. Yep, so after this, okay, so at this point, you would, a takeaway would be that in base R, you call these small little functions to do all the work within the plot. But there are tons of different types of plots, right? There are box plots, bar plots, histograms, density plots, and whatnot. And you would think that, okay, if I'm using these really small functions to produce these plots, do I really need to know hundreds of those functions? And it turns out that a set of things you might want to do for a plot is really quite limited. So here I tried to provide a set of functions that would be quite sufficient to produce almost any kind of plot. And in the next slides, I will try to demonstrate how you could use those functions to really recreate the plots you want to see. So just as a simple example, here we first create a checkerboard pattern. So we create some variables. Don't worry about these too much, but these are basically the centers of the rectangles. We will have many rectangles on the checkerboard, and each of these rectangles will have an X coordinate and a Y coordinate. So those two variables just called that. Then there is a bit of a boilerplate, which is always has to be done. You always have to request a new plotting window, and you always have to set the coordinate system on that window for any plotting to be done. So that this does that. And then with just one function called to this function rect, which draws a rectangle, you can produce, or you can actually draw all the rectangles in a single go. So this function accepts just a few arguments. Basically, you provide coordinates for the lower left side of the rectangle and the upper right corner of the rectangle, and it draws a rectangle. And if you provide many, it will draw many. So with just a single function call, which is vectorized, we can add a lot of objects of the same type on the plot. Now, moving on to a more realistic example, for example, bar plot. Here, we will try to produce a bar plot for US population growth. So again, we extract the needed variables to X and Y just for convenience. So X here would be time in years, and Y would be population, I think, in millions. Once we have that, again, we have our boilerplate code, which is give me a new plotting window and set the coordinate system. After that, we can start producing the plot. So in this case, we want a bar plot. What do? We call rect, basically to draw a rectangle for every population value for every year. We already have a thing that resembles a bar plot pretty well. Then we might want, for example, to add the actual values in text on top of each bar plot. And here, text function does that. And there is this pos equals 3 argument in the fourth position. And the 3 again just specifies the position, like I mentioned with the axis. 1 is the bottom, 2 is the left side, 3 is the top. So we want the labels on top. So we say 3 and they will be on top of the actual values. Finally, we add the years as an axis text, and also the actual values for the y-axis as the axis text. And then, okay, maybe we still need the title. We can add the title. And here is our bar plot. It's made from scratch. It uses no extra libraries, no wrappers, just 5 lines of code, really. Then another example. For example, you might want to produce this plot called parallel coordinates plot, which is kind of a bit fancy. So here, palette, okay, so this function, what it would do is it would change the colors represented by numbers. So if I draw a color and I say color equals 1, typically R interprets that as black. But here I say don't interpret that as black, interpret it as blue. And number 2 as red, 3 as orange. So just some preparation. Again, boilerplate, I request a new plotting region and provide a coordinate system. Then, okay, I add a grid just on the y-axis. So we have these grid lines. And then I provide this axis. The parallel coordinates plot basically joins lines for every variable. So in the iris data set that we will use here, we have 4 variables. So I add these 4 lines that will be joined. And then I add all the lines again with a single call. Then I use this mathLines function, which draws lines from a matrix. But you can do this just with lines as well if you go over each column. So I already have the plot. Now what I need to do is just annotate it. Okay, so I add y-axis text with the axis call. And then I add text for all the variables that were used in this plot. So again, just another function called margin text. And I have my plot. Okay, maybe still I add a legend, right? I find a convenient place for a legend. And okay, one more trick here is I use factors for colors. What it does is it interprets them as integers. And I already changed the palette. So the factor, the first factor would be colored in blue, second in red, third in orange. And what this does is it makes sure that the color placement between the plot and the legend is always consistent, because factors, I never reordered them. So the same factor will always be represented by the same color. Yep, so we have another plot. And one more example is this dual coordinate plot. This is a bit in poor taste, but some people do this. You might have a plot that has 2 different y-axes. So that's an example of a plot like that. And we will be using this empty cars data set, and we will be showing displacement on the x-axis and miles per gallon and horsepower on y-axis. So again, some boilerplate, plot new, plotting region as always. We add the points for the first y-axis and add the actual axis label. And now the hardest part of this plot is I need to add the second y-axis that uses different numbers. What do? So I change the coordinate system in the middle of the plot by calling plot window again, and now providing different values for the y coordinates. And right after that, I add my second set of points in different color, and I add axis annotation on the right side now. So the plot is already done. And now I need just to annotate it again. So, okay, I add axis on the axis values for the x-axis. I maybe add box around the plot and some annotations in different colors. Yeah, so this plot that on the first impression might look a bit complicated. You know, you need 2 different y-axes. If you do base plotting really from this fundamental like elements, it becomes quite easy and very intuitive, in my opinion, at least. And the final example is this correlation plot. So this kind of plot you might be familiar with if you use packages like corplot or maybe ggcorplot. And it tries to present correlation values from a data set in the form of circles. So here we will be using empty cars data set, and this cars variable just calls the correlation matrix. And calls variable in the second line, don't worry too much about the syntax, but it basically obtains a color for each correlation value that goes from blue to red. Again, some boilerplate. We initiate our plotting region. With the call to rect, we add this grid of rectangles, and within each of a cell in each grid, now we will plot our correlation values. So we do that with another function call, which is symbols. And with symbols, we can control what kind of symbol we plot. In this case, it's a circle. We can control the colors and the sizes of these circles. So in this case, I just make sizes proportional to correlation values. And we have our plot. Only thing that is left to do is just to annotate it. So we add text for each variable, and we have our plot again in maybe 5 lines of code. The actual code that does the plot and annotation. Yep, so that's my final example. And the takeaway from this, I would say, is that base plotting has this kind of mystique about it, where users are never really introduced to it properly, I think. And it's a bit sad, I think, because really it allows you to replicate any kind of plot. So if, for example, you're working as a person who does plots for some company, and you have a designer that makes templates, and your job is to produce a plot that resembles that template really thoroughly, exactly. This type of plotting, like base plotting, I think would be the perfect tool for that, and it would just take a few lines of code. And you can actually do a lot of crazy things here. So, for example, if you want to have a plot that instead of having 2 y-axes, it has 5 different y-axes, that's fine. It's just 5 more lines and you will have. Yep, so thank you for listening and hope you enjoyed. In this talk, I mainly presented some of the corners of R I found during my work that seemed interesting to me, and some ways in which I tried to utilize those corners. And I hope some of you maybe got some inspiration to try using them for maybe different purposes. I use them for providing a theming system and this package inops, but this doesn't mean that they can only be used for that. There are a lot of other users that I probably didn't think about. And this talk was mainly a compilation of 2 of my articles. And if you are interested in that and want to find even more stuff about even more lesser known features or more information about base plotting, you can check that out. So that's it.